Okay, good afternoon. Welcome to EE222. We will continue our studies on sequence detectors. So the thing about sequence detectors is you just got to do lots and lots of problems. You got to do lots and lots of problems. And the good news is, for the purpose of your quiz / short test, we can't give you a 15-bit sequence because that's going to take 15 states. Yeah, so we're going to be realistic. It's either going to be a 3-bit sequence or a 4-bit sequence, or maximum, absolute maximum 5-bit sequence, right? For your final exam situation, for your final exam situation, for your quiz / short test 2 situation, we can't give you much anyway, right? Because it's a very time-consuming process. But yes, for your project, we have given you, how many bits are there? There are 4 bits each, right? Now, for those of you who want to speed up and are hungry to finish their project, that's good on you. I'll show you what you can do. You can okay, so if you want to go ahead and do your project quickly, you come to the week 12 sequence detector, pattern detector lecture. So basically this week and next week we'll be doing sequence detectors, design problems on sequence detectors, or design problems on sequence generators, one or the other, right? So we're going to give a good mix of these problems. The problem to look at if you want to do it, if you want to get ahead in class, is this one here, number 4, problem 4, right? So that's problem 4, and you can go ahead and, have a look at it.
If it's okay with you guys,
yeah. All right. So this was done last year online, right? So these problems were done last year online, and if you want to look at the write-up, whatever that Word document was, you can have a look over here, and you'll see problem number 4. So your diagram for your project, because it's 3 bits. Let's look at question 4. What was the question 4? Question 4, it says, design a sequence detector which gives an output of 1 when any of the sequences shown below are detected. The circuit resets after getting a sequence. All right. Use a milli machine model. Is in your problem number 2. I'm talking about project problem number 2. Is it milli machine or did I say more machine? Milli machine. And was it 3 sequences? Was it 3? You have to detect any of the 3? Okay, let me just open it up. Don't worry, I'll open it up. Okay, let's come here. There we are. Okay, and of course the demonstration is next week Friday. If anybody wants to get a head start and demonstrate already, that's fine. So ABC, okay, ABC. So there's 3 sequences given, 0. So for example, whoever this guy is he here in class? No, not here. Okay, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0. All right, okay. The problem was any of the 3, assuming that overlapping sequences are allowed. Okay, overlapping is allowed. Okay. Anyway, the point being that problem 4 over here in the lecture, if you want to go ahead, have a look at my video. This is the working table. It is not absolutely necessary. You can go straight to this. You can go straight to this. All right. Okay. So this is what your state diagram will or might look like in the end. This is what your state diagram might look like in the end. Right? So just to give you a heads up. Once you got your state diagram, after that everything is downstream from there, because all you got to do is you got to convert that into a state table. So let's look at problem number 1, which we did last week. Last week on Friday we did problem number 1, which was this one here, guys. Right? That's problem number 1. From that you do a state assignment. Right? State assignment you can do straight within this thing here, 0, 0, 0, 1, 1, 0, 1, 1. Then we go ahead and get your state table, then you get your K-maps and your equations, and then your circuit. All right? Guys, and if you don't understand what I'm saying, let's say you don't like my concept of having this thing called the working table or analysis table, that's fine. You can look at other people's videos. Generally, you should have a working circuit, right? Sometimes there can be a variation in answers, but the circuit will be working, right? Should be a working circuit. All right, let's do another problem. Let's see what do we have here. Problem number 1. I did a replica of problem number 1 last week. So this is 1010. Let me see if I have something. All right. This is 1010, in problem number 2. Okay, problem number 2 is 1010. Let's try. How about we try 0111? So I'm going to leave this for you. You can. This is already available, right? This is already available. The video is there. You can follow the video. I'm going to do 0111 for you, which is not available. So somebody who missed the class, they'll be the one who missed out. All right. So let's come to the thing here. The particular document camera. Go. So write that question down. Write that question down. Example number 2, and then change this to 0111. 0111. Right? So I'm giving a different problem. I don't want to repeat problems. Right? Why should I repeat this problem, which you can watch in your free time? The video is there, the working is there in the Word document. So it's the same problem, but we're going to do 0111. Okay, today is, what's today's date, guys? Week 12, lecture 2, and today is the, guys, today's date is the 15th. Okay, so problem number 2. So problem number 1 was a replica. Problem number 2, I'm just going to copy that down. Milli machine. To detect, what did I say? 0111, right? 0111. Overlapping sequences are allowed. All right, okay, let's go ahead. Right, so maybe the lights are, maybe I turn off the lights. Sorry, 1 second, please. Okay, so it can pick up my hand. Okay. All right. But I can't zoom. What's wrong with this thing here? All right. I can't zoom. Okay, I hope you guys can read that. Is that visible, guys, or a bit too much or too less? There's nothing responding on this machine. At least the camera is working. All right. Okay, is that all right for you guys? Can you see that? I can't zoom in. I don't know why. None of the buttons are working. Okay, let's go ahead. So we've got to detect 0, 111. It is a milli machine. In a milli machine, because it is a milli machine, right? Let's count the bits. 0, 111 is 4 bits. And because it is a milli machine, right? Because it is a milli machine and we have 4 bits, right? That means we need 4 states, right? Now think of it like this. In order to detect 4 numbers in a particular sequence, you need to have 4 stages to go through it, right? Okay, that's the easy part. Now in the Moore machine, because milli machine is what? The output is determined by input is blended in with the output, right? Okay, in the Moore machine, right? What is the Moore machine? Moore machine, the output is independent, right? In the Moore machine, the output was independent. Okay, in the milli machine, the input was going together with it. Okay, now, so we have 4 states. If this question was changed to Moore machine, if that question was changed to Moore machine, so note this down so that you have an awareness, the answer would have been 5 states. States, remember we did states, right? 5 states means, what does 5 states mean, guys? That means in our state diagram, how many bubbles will there be which are actually being used? If it was a milli machine. If it was a milli machine, right, how many bubbles will be in our state diagram? Right, this is where your earlier sequence generator problems comes in. In our state diagram, you know what is state diagram? How many bubbles, how many circles will there be? 4, right, milli. If it was more, it'll be 5. 5 actual use states. Now, what is the good news about 4 states? 4 states. If you were to do 4 states, how many flip-flops do you need? You need 2. In order to achieve 4 states, you need 2 flip-flops because each flip-flop is 1 bit. In order to gather 4 states, it's 2 to the power of 2, 4. Now, this is the game changer. If this was a Moore machine, how many states will we need? It's always milli plus 1. The answer for milli plus 1. So Moore will always be 5. Let's now change the question. What if this was a 3-bit sequence? Like 0, 1, 1. If it was a series 0, 1, 1, for milli, how many states would we need? 3 states. How many? Okay. 3 states can be accommodated by how many flip-flops? 3, 1 or 2? 2 flip-flops. So if there's 2 flip-flops, how many possible, maximum possible states are there? If there's 2 flip-flops, how many maximum possible states are there? 4. So if it was just 0, 1, 1, what happens then? Is there an unused state? Yes, there is. There is an unused state. All right. But what about if it was a more? If the question was 0, 1, 1 and do more? I hope you're noting this down. This is very fundamental differences, right? If it was 0, 1, 1 and build a more machine, right? You would need 3 initial states plus 1 state to take care of the output, right? 1 final state. So it's 3 plus 1. Milli, the answer for milli plus 1. So in more, are there any used states? If this question was more, 0, 1, 1. No. All right, now, let's consider this question. Let's consider this question. If it was 0, 1, 0, 111 now, 0, 111, and the question said milli, we know it's going to be 4 states. 4 states, that means 2 flip-flops. Oh, guys, maybe I should give you, well, that's not part of the question, but you can say use T flip-flop, but we're not going to go all the way. We just want to get to the state diagram. Once you get to the state diagram, it's all standard procedure. You convert it to a state table, Carnot maps, equations, right? Circuit. Right, guys. If this question said more, instead of milli, it said more, all right? If instead of milli, it said more, tell me how many states would be required to accommodate? 5. Milli, so answer for milli plus 1, number of bits plus 1. So 4 bits plus 1 gives you 5. Now, in order to accommodate 5 states, how many flip-flops do you need? 3 flip-flops. So, how many spares do we have then? How many unused? If 5 is used, 3 become unused. So you have unused states, right? So please be careful about all these things, eh? Used state, unused state, and so forth, right? Generally, unused states, you can ignore them, and it won't, in sequence detectors, it won't affect the problem. You don't have to, in sequence generators, we have to route our unused state to a particular state, right? In sequence detectors, because the input is being fed in, right? You can ignore the unused states. Anyway, let's come back to this question, guys. Let's come back to this question. If this, I'm just going to say, if this was a Moore machine, then it'll be 4 plus 1 equals 5 states, which would be 3 flip-flops, which would also mean 2 to the power of 3 is equals to 8. 8 maximum possible states from 3 flip-flops. 8 minus 5 used is equals to maximum 8 minus 5 used is equals to 3 unused states in Moore. All right. Okay, let's start the problem. We've been talking side stuff, but let's start the problem. So this is what I called the, I call this the working or the analysis table, right? Okay. Now let's start off. Something called the state. Guys, always use a ruler, all right? Always use a ruler, right? Look at this, past input string, past inputs, or sometimes they call it the, what did I call it last time? I had a very long name over here. Receiving input or past input string. Yeah? Okay, past input string. Or sometimes they call it the receiving input. What else did I do? I keep on forgetting my own table. The current possible inputs. Current possible input. And this is what? X. And we know that it'll be only 1 bit. Right? Current possible input string. Next, state system output. Let's call it Y. All right. We always start off with A. If you don't like to call it A, let's call it, we don't have to always call things A, B, C. All right? Just to give you an idea, you can always name the states apple, pear, apple, pear, carrot, whatever, cucumber, whatever you guys like to use. All right? Okay. Now, All right. Our friend over here is laughing. Cucumber. I don't know why. Okay. All right. Okay. Now the past, let's start off with A. Okay, I'm going to change it. I'm going to play around with things here. I'm going to say, I'm going to call it state I'm going to call it stage 0. Stage 0. All right, let's give it a long name, just to give you an idea. Stage 0. Pass input over here is system is empty. There's nothing there. It's the first round, right? We also call this stage the reset stage, right? Obviously, from here, we know the answer is 4. So that's why I've drawn 4 over here. All right, system is empty. What else did I write last time? Empty. The system, this is the first bit to be processed by the system. System is blank, blah, blah, blah. All right, you guys get the picture. Okay, so now, current possible input. So over here, look at this, guys. You can either be a 0 or a 1. All right, you can either be a 0 or a 1. Fine? Okay, you can either be a 0 or a 1. All right. Now, current possible input string. Because this one was empty, we merged these two. We merged these two rows, right? Okay. So empty together with 0 will be only a 0. Empty together with 1 can only be a 1. Right? This is where we start. So we populate all this. So that is stage 0, stage 1, stage 2, stage 3. Why did we have to go 0, 1, 2, 3? Because there are 4 states. Okay, so 1, 2, 3, 4. Stage 0, 1, 2, 3. That's the reset stage. Anything goes wrong, you go right to the beginning. Okay, now. So this is the table, predetermined table. You start off, this is your blank table, what you call a blank table. We haven't really started doing the calculations yet. Your kickoff table is this, right? Now we start thinking. All right. What is the sequence? 0, 111, right? 0, 111. All right. 0, 111. Now, if in the first instant you get a 0, right, your current possible input string becomes a 0. Does that match the first line? Yes, 0. 1 is? No, it doesn't go in, right? So because this guy qualifies, he goes to what? Stage 1. Yeah, he goes to the next stage. What is the output in this case? Is the output 0 or 1? It still remains a 0. All right? In fact, the output will always be 0 until we hit 0, 111 in this line. Right? Until we hit a 0, 111 in this column, then we'll have a 1 out over here. Okay, now 1. 1, we stuck. Right? We can't progress. So we'll be stuck at stage 0. Right? Now. Okay, next line. So 0 progressed. So this fella comes down here. 0 progressed downwards. 0, 0, 0, 1. See what I've done? 0 marries 0, 0 marries 1. 2 possibilities now. It can either marry a 0 or a 1. All right, now. 0, 0. Is the first 2 bits 0, 0? No. So, falls out. 0, 1 qualifies. Right? Qualifies. So we can say this guy qualified, this guy qualified. All right. 0, 1 qualifies. 0, 1 qualifies. He goes to the next stage. What's the next stage? Stage 2. 0, 0. Can we recycle this? That is the hard part now. Okay. Stage 2. But have we got the 4-bit sequence? No, not yet. So that's out. Obviously, this guy failed, so he's out, obviously. Now, this is the tricky part. The tricky part is what do we do with the failure? We want to recycle it. If we want to recycle it, this 0, 0, where does it go? Where can we say the 0, 0? is that 0 useful at any stage? Yes, we used a single 0 over here. So we stay at stage, right? You stay at stage 1. You see this 0? So that last 0 can be recycled over here. Right now, okay, now what qualified? 0, 1. So we write down 0, 1 over here now. Right? That comes down here. Now 0, 1 marries a 0, becomes 0, 1, 0. 0, 1 marries a 1, becomes 0, 1, 1. Now let's have a look at this. 0, 1, 1. Is that being used in our sequence? Yes, 0, 1, 1 is in. This is out, so this is in. All right? Okay, so because this guy is in, what do we say? He goes to stage 3 now. But the output 0, 1, 1, is that identical to 0, 1, 1? No, not yet. This one was out, so obviously he falls to 0. 0, 1, 0. What can we recycle from there? Can we recycle the 0? Or can we recycle the 1, 0? No, the only thing we can recycle is the 0, which will fall into, where did we find the 0? Stage 1. All right, now let's see. This guy qualified. 0, 1, 0, 0, 1 comes downwards. Marries a 0, so that's 0, 1, 1, 0. This one marries a 1, becomes 0, 1. Obviously, we know 0, 1 is exactly what we were looking for. So our output becomes 1. Our output becomes 1, right? Okay. And obviously, in the other case, the output was 0. Now, obviously, this guy is out. So out, all right, okay. Okay, now, what do we do here, guys? All right, this 1, is the 1 useful ever? No way. 1 is never useful. So what do? We can say we return him back to stage 0. And is the 0, 1, 1, 0, is that useful ever? Stage 1. That's it. From here, right, you guys got all this? Take note of it, and then we'll draw the state diagram. And then I'll try and do this entire problem for you guys, right? Right, everyone happy with this? This is only the working table. You will see some YouTube videos, and I'm only doing this just for teaching purposes, guys. Even sometimes you can call it the teaching table, all right? Okay, it's only the teaching or working table, only to show you guys. All right, now, so how many states was there? There was, how many states were there, guys? 4 states. We call this stage 0, stage 1, stage 2, there we go, stage 3, 0, 1, 2, 3. All right, now, you guys look at your table, right? When we were on stage 0, and our input, this is the input line. That's why this line is important. Otherwise, you could have jumped here. When we were on stage 0, input was 0, output was 0. And where did it go to? Stage 1, right? Stage 0, input was 0. It went to stage 1. Input was 0, output was 0. Is that? Okay, now next one, guys. Stage 0. Stage 0. Input was 1, output was 1. It stayed at stage 0. Input was 1, output was 0. It stayed at stage 0. Stage 2. Stage 1, input was 0, it went to stage 1 again, it stayed at stage 1. And if input was 1, it went to stage 2. Right. If input was 1, it went to stage 2, output is 0. And if input was 0, output was 0. So, you know, the good thing about these things are that they always, you will only get an output of 1 only once. Right now, stage 3, stage 2. If input was 0, you went to stage 1. If input was 1, you went to stage 3. If input was 0, you went to stage 1. And if input was 1, you went to stage 3. Now, in the last case, stage 3. If input was 0, you went to stage 1. If input was 1, you went to stage 0, but with output of 1. Right? And the other one was... Have I missed out any of the other lines? No? All right. Okay. So now we come to our state table. So for every stage, there should be 2 inputs. For 1, 0. 0, 1. 0, 1, 0, 1. There we go. All covered. 8 lines. So altogether, 4 states, so 8 lines. 1, 2, 3, 4, 5, 6, 7, 8. Right? Okay. Now, state diagram. Oh, sorry, not state diagram. State table. This is the state diagram. Okay. Let's call it, how many flip-flops? 2 flip-flops. Let's call it Q1, Q0, input X. I'm deliberately drawing it like this, guys, just to show you that you can shuffle. You can shuffle. You can put the X over here or put the X over here. In the end, all possible combinations are covered anyway. Right, what flip-flop are we using, guys? T. Mr. T. And then what do we have? Q1 star. I'm pulling a shortcut here. You usually have another heading over there, what state it is and all this. What did I say? Y, right? Okay, all possible combinations. And what we can say is, oh, you may be wondering that, hey, what is this? You do state assignment. Usually, sometimes, we do state assignment by doing a table like this. Right? You make another table called the state assignment table and say stage A is 0, 0. Right? So you can make the table, but you can just do this. Right? I do the state assignment straight away. Because by now, you've done bigger problems, hey, there's only possible state. And even if, let's say, you wanted this to be 1, 0 and that to be 1, 1, that's fine. Right? So long as you've got a system in place and consistency. Right? So now, 0, 0, 0, 0, 8 possible combinations. Everyone happy with that? Guys, this is a shortcut table. Let me warn you that this is a very shortcut table. There's supposed to be something all over here, current state or present state, system input, flip-flop inputs, next state, system output, the line on top. Please make sure you fill that out, all right? Okay, I've done a shortcut table to save time. But you guys get the idea now. We've done so many of these tables that you are so used to it now, all right? Okay, now you guys read out for me. One reason why I like to put it this way is you can read it easily. Because 0, 0, right, we can just say, hey, this is Q1, Q0. Even if somebody placed Q0 and Q1, and then your table was Q0, the other way around, you just have to follow the sequence. So long as you follow the sequence, you'll get the same answer. All right? Okay, now, let's now see. 0, 0. See, so 0, 0 goes to what? 0, 1 when input was? Tell me, guys. Help me out now. 0, 0 goes to? 0, 1. Input is 0, output is 0. Okay, next one, guys. 0, 0, input is 1. 0, 0, input is 1, stays the same place, right? Output is 0. 0, 1 goes to 1, 0. Oh, no, 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 no. Okay, 0, 1 stays at 0, 1. 0, 1, 0, 1 stays at 0, 1. Input is 0. Output is 0. 0, 1 moves to 1, 0 if input is 1. You have to be careful because I've changed the arrangement of the table, right? So long as this section is in the beginning. 0, 1, if you have an input of 1, will go to 1, 0, and the output will be 0. Okay, 1, 0 will go to 0, 1. If the input is 0, output is 0. 1, 0 will move to 1, 1. 1, 0 will move to 1, 1 if input is 1, but output will remain 0. 1, 1 will go to 0, 0. 1, 1 will go to 0, 0 if output is 1. I'm doing the last line. 1, 1 will go to 0, 1 if input is 0 and output will remain 0. Set? Anybody got something different? Maybe I made a mistake. I'm doing this problem live, right? I'm doing this problem straight away. I made the bit code. Okay, all right. Now, next one, next line. T. Can somebody tell me T? Let's look at your, now we bring out your tables. Do we have your table here somewhere? Table. By now, you use so much of the table that you become used to it. Okay. Table. T flip-flop. Excitation table. Excitation. You know your current, you know your past. So, what do we say? What do we do, guys? So, I'm looking at the table. I'm trying to fill up. Yeah? Last row. Both 1. Input is 1. Oh, yes, that's right. Goes to 0, 0. Thank you. That's right. Goes to 0, 0. All right. Thank you. So you have to be very careful. All right? Most of the errors, in fact, happen when you go from there to there. All right? You have to be very careful. Copying errors, basically. Okay, now. Right, let's go. Let's do this. 0, 0 will give you 0. 0, 0, 0. 0, 0, 0. 0, 1, 1. 1, 0, 1. 1, 1, 0. 1, 0, 1. 1, 0, 1. Let's move to the second one. 0, 1. 0, 1 is this one, eh? 0, 1 is 1. 0, 1. Oh, sorry. 0, 0. 0. 0, 1, 1, 1. 1, 0. 0, 1. 1. 0, 1. 1. 1, 1. 0. 1, 0. 1. Okay, there we go. All right. Okay, now. Okay, it's not over yet. It's not over yet. We find the flip-flop inputs, T1. We draw a Carnot map. Check this out. Q1, Q0, and this is X. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. T0, Carnot map. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Q1, Q0, X. Why did I put it in that order? Because that's the order that my table is in. So it makes it easy. Output, Y, Carnot map. Okay, let's fill it up. Let's fill the Carnot maps up. 0, 0, 0, 1, 1, 0, 1, 1. Let's fill up T0, 1, 0, 0, 1, 1, 1, 0, 1. And the last one would be 111. Usually in sequence detector, there's only 1, 1. Okay, now let's group it up. One group that way, one group that way. Can we do anything here? One group that way, one group that way, one group that way. This guy stands alone.